For this video on metallic bonds, I will assume you've seen my videos on the periodic table and van der Waals bonding. Ionic bonds, covalent bonds, and metallic bonds are what we most commonly think of as chemical bonds. All three types of bonds involve the exchange or sharing of electrons. Atoms exchange or share electrons to fill their outermost s and p electron orbitals. A filled octet of electrons in its 2s and 6p orbitals places the atom's electron cloud in its lowest energy state. Of the 118 elements in the periodic table, about 80 elements, or about 2/3 of the elements, are metals that can form metallic bonds. In the periodic table in the figure, all the elements shown in red are metals. In metallic bonds, the metal atoms form a lattice or crystal structure. The kernel of the atom is the nuclei and all the electrons except for the valence electrons or s and p electrons in the outermost electron shell. The metal atoms in the lattice give up their valence electrons to the lattice. The metallic bond is formed by the mutual sharing of all the electrons present in the lattice. The most primitive way to think of a chunk of pure metal is to think of it as a single molecule formed of positive ions in a sea of electrons. It is the wave nature of electrons that they are present at varying densities in all parts of the metal molecule at the same time. The electrons in a metal are said to be delocalized. This delocalized behavior of electrons in metals is quite different from ionic or covalent bond, where the electron belongs to a specific atom or is shared between two specific atoms in a covalent bond. This non-localized behavior allows the metal atom kernels to shift position within the metal structure without destroying the metal bond. This freedom of movement gives the metal object properties such as ductility and malleability that do not exist in objects that might be bonded ionically or covalently. Nuclei and ionically or covalently bonded objects must remain in the same local position relative to the nuclei that they are bonded to or share electrons with, or else the bond is broken and the object breaks apart. A shift or slip in the metal kernel position does not necessarily break the metal object apart. In their efforts to refine a theory of metallic bonding, quantum physicists first proposed the free electron model and then extended the theory to the almost free electron model. Both theories fall short of being correct. At this writing, there is no refined theory that completely explains how metallic bonds work. A full understanding of how metals bond is at the limit of human knowledge. The properties of metallic bonds must still be determined through experiment. The non-local nature of metallic bonds gives metals their properties of tensile and compressive strength, as well as ductility and malleability, thermal and electrical conductivity, and their melting and boiling points. Most metals have good elastic and plastic properties. An elastic limit is how far a material can be deformed and then returned to its original shape. Beyond the elastic limit, most metals become plastic. Plastic means the material can be deformed without tearing or crushing. At the plastic limit, a material will crush or tear. Ductility is a material's ability to plastically stretch without being ripped apart. Platinum is the most ductile metal, but it is very expensive due to its rarity. Copper is ductile, common, and conductive, so it is often drawn into thin wires used to conduct electricity. Malleability is a material's ability to deform plastically without shattering. Lead is very malleable and can be pounded into thin sheets. Gold is the most malleable metal and can be hammered into gold leaf just 100 nanometers thick. Gold has been pounded into leaves only 30 nanometers thick. A gold atom has an atomic radius of 144 picometers, so a diameter of only 0.3 nanometers. So a sheet of gold 30 nanometers thick might be 100 gold atoms thick. By contrast, carbon atoms have an atomic radius of 71 picometers and have a diameter of around 0.14 nanometers. A human hair might be 100,000 nanometers thick or 600,000 carbon atoms thick. Tensile strength is a material's resistance to being pulled apart. Compressive strength is a material's ability to withstand pressure or to being crushed. Strengths of materials are usually measured in megapascals in metric or pounds per square inch in British units. Many tables for metal will give both yield strength and an ultimate tensile strength for a metal. Under a load below its yield strength, a material will stretch elastically and then spring back to its original shape once the load is removed. If the load is greater than the yield strength, the material will deform plastically into a permanently deformed shape. If the load is greater than the ultimate strength, the material will tear apart. Metals have different strength depending on formation, heat treating, and work hardening. Steels and structural aluminums are graded with numbers. Metallurgists use alloys, heat treating, and forging or work hardening to increase the metal's toughness. Embrittlement is to be avoided. Brittle materials like glass have a yield strength that is too close to their ultimate strength. Brittle materials break or shatter rather than bend or deform plastically once their yield strength is exceeded. Alloying materials such as carbon or chromium are often added to iron to form a much stronger steel alloy. Magnesium or silicon are common alloying agents in aluminum alloys. The alloy atoms are larger or smaller than the base metal atoms, and so block the base metal layers from slipping past one another. Heat treating involves quenching a hot metal in water or oil to cool it quickly to lock its crystal structure in place. Quenching must be followed by tempering or leaving the metal to soak at a higher temperature to allow internal stresses that would embrittle the metal to relax and be relieved. Work hardening involves pre-bending or plastically deforming the object before use. The work hardening allows the metal kernels to slip past one another during the forging process so that the pre-slipped kernels will be resistant to further slipping during use. Care must be taken that the work hardening is not so extreme as to embrittle or fatigue the metal. An example of how alloying and heat treating can increase the strength of a metal might be a comparison of a low-strength untreated metal against a high-strength treated alloy of the same base metal. Annealed aluminum is heated then slowly cooled to leave a stress-free and relatively soft form of aluminum. Annealed aluminum 2024 has a yield strength of 76 megapascals and an ultimate strength of 186 megapascals. The heat-treated aircraft aluminum alloy 2014-T6 has a yield strength of 414 megapascals and an ultimate strength of 483 megapascals. Cast iron ASTM A-48 is a relatively weak iron with a yield strength of 130 megapascals and an ultimate strength of 200 megapascals. Steels are iron alloys that can achieve great strengths. Chromium vanadium alloyed steel AISI 6150 has a yield strength of 620 megapascals and an ultimate strength of 940 megapascals. Engineers have a wide range of choices for building materials. Engineers must be careful that manufacturers do not substitute weaker grades of material when they design a structure to be made of a stronger grade of material. Pictured is a chart of materials showing their yield strength, ultimate tensile strength, and density. Note that other common building materials do not come close to the strengths of aluminum or steel. Some carbon fibers can approach or exceed the tensile strength of steel because of their strong carbon bonds. We can see in the table that the annealed aluminum, cast iron, and copper are weaker than their heat-treated alloy forms. Heat-treated aluminum alloy 2014-T6 has almost 5 times the yield strength and twice the ultimate strength of annealed aluminum 2024. Structural steel A36 has almost 1.5 times the yield strength and twice the ultimate strength of cast iron A48. Chromium vanadium steel 6150 has almost 5 times the yield strength and 5 times the ultimate strength of cast iron A48. Heat-treated aluminum alloy can be as strong or stronger than low alloy structural steel. High alloy steels are stronger than any grade of aluminum. I put copper and bronze in the table for historical reasons. Copper is the first metal that ancient humans used for tool making. The earliest archaeological sites of copper mining and smelting include the Vinca culture sites in Serbia, Eastern Europe, maybe around 5500 BC. Middle Eastern sites for evidence of early copper use include Yerem Tepe in Iraq and the Timna Valley in Israel, both before 6000 BC. Before copper was first smelted around 7000 BC, all tools were made from naturally occurring rock, bone, horn, and wood. Some lead has been discovered at 6000 BC sites at Yerem Tepe. Lead is too soft to make sharp-edged tools. The transition from the New Stone Age or Neolithic to the Copper Age or Chalcolithic occurred around 4500 BC. Between 7000 BC and 4500 BC, tools were created from a mixed bag of stone and copper. Copper is soft and only slightly better than stone for making cutting tools, knives, and axes. Ötzi, the Iceman, the frozen body discovered by hikers in the Italian-Austrian Alps, is thought to have lived around 3300 BC. The copper axe found with Ötzi the Iceman is thought to have been made from copper ore mined in Tuscany, central Italy. Around 3200 BC, it was discovered that by adding 10% tin into the smelted copper created the copper alloy, bronze. From the table, we see that bronze has twice the yield strength and 1.5 times the ultimate strength of pure copper. Tin is rare, and suitable tin mines in ancient times only existed on the Czech-German border and on the Cornwall Peninsula in Britain. Tin from Cornwall was shipped all the way to the Middle East through the Mediterranean Sea. The discovery of bronze ushered in the Bronze Age that lasted from 3200 BC to 1200 BC. Iron was difficult to work and only replaced bronze as a tool-making metal around 1200 BC when the Bronze Age collapse resulted in a tin shortage. The tin shortage was due to a simultaneous collapse of the tin trade through Central Europe and across the Mediterranean from Cornwall in Britain. Speculations about the causes of the Bronze Age collapse include Egyptian references to outside invaders they called the Sea Peoples. The table also contains the ultimate strength of non-metal building materials, including concrete, wood, and carbon fiber. All three of these materials are covalently bonded. None has a real yield strength. Wood, both pine and oak, are stronger in tension than in compression. Loads parallel to the wood grain are assumed. We can see that alloy metals are 5 to 10 to 20 times stronger than wood in all cases. Concrete is 2 to 3 times stronger than wood in compressive strength. Metals have a compressive strength that is 10 to 20 times greater than concrete. Concrete has almost no tensile strength compared to other materials. The last material on the table is carbon fiber. Carbon fiber can be stronger in tension than many steels. Carbon fiber is beginning to replace steel in many applications where low weight and high tensile strength is required. Carbon fiber has its downsides. Although it does not rust like many steels, it does break down with age and especially with exposure to ultraviolet light. From the table, we can see that without high-strength metallic bonds, we could not make most of the tools and structures that create our modern civilization. If metallic bonds did not exist, we would still be living a Stone Age existence. Two more great things about metallic bonds and metals in general is they are great electrical conductors and heat conductors. Certainly, 21st century civilization could not exist without metals' electrical and thermal conductive properties. Metals are good thermal and electrical conductors because of the free electrons in the metal crystal. Temperature is just the vibrational speed of the atoms in the material. In a simple explanation of thermal conduction in metals, the free electrons bump the atoms vibrate faster, so they increase in temperature. The atoms increase the speed of adjacent free electrons. The adjacent free electrons bump the next row of neighboring atoms and so increase their vibrational speed and therefore their temperature. And so by this bumping process, the heat energy expands out from the heat source or from the higher temperature into the rest of the material. Insulators such as plastic and wood do not have this sea of free electrons, which is why they do not conduct heat as well as metals. Electrical current is also carried by the free electrons in the metal lattice. Electrons do not move from the power source to the load or use point. Only the electrical signals travel the full electrical circuit. The electrical signal in a conductive material can move at nearly the speed of light. The velocity of individual electrons is actually quite slow, only a few meters per hour or a few hundredths of a mile per hour. The speed of the electrons is known as the drift velocity. We can make an analogy of the electrical signal to an ocean wave. An earthquake in the middle of the ocean can trigger a tsunami wave that can move at 600 miles an hour. The wave is the signal and the water molecules are the carriers of the signal. The water molecules themselves hardly move at all as the wave passes. The water molecules only bump the next water molecule to carry the energy of the signal away from the source of the signal, in this case, the earthquake energy. Likewise, in an electrical conductor, the free electrons only drift into and bump the nearby free electrons. The electrical signal itself and the energy it carries transfers from one electron to the next. The signal speed is independent of the speed of the individual electrons that carry the signal. Like the water molecules carrying the wave energy, the electrons carrying the electrical energy do not need to move very fast or very far to carry the signal and its energy. Individual electrons only carry the signal to its neighboring electrons that continue the transmission of the electrical signal. The ease at which a material can transfer heat is its thermal conductivity. The ease at which a material can carry electricity is its electrical conductivity. Both conductivities have an inverse property called resistance. Materials with high conductivity and low resistance are used as conductors. Materials with low conductivity and high resistance are used as insulators or resistors. In metals, a good thermal conductor is usually a good electrical conductor. In nonmetals, materials that are good thermal insulators are generally good electrical insulators. The exceptions in nonmetals are carbon compounds such as diamond. Diamond is a great thermal conductor, better than any metal. On the other hand, diamond is a very poor electrical conductor. The opposing properties of diamond make it a promising material for use in computer circuit boards. These circuit boards need a material that can readily transfer heat out of the circuit board, while at the same time electrically insulate the fine wires carrying the electricity from each other. We can see in the table that both silver and copper have very high thermal and electrical conductivity. This explains the extensive use of these materials in electronics. As copper is more common and less expensive than silver, copper is the dominant material used in making components for electricity transmission. It is a gift from God that copper is plentiful, a good electrical conductor, and also highly ductile so that it can be drawn into long wires. I don't think our electrical grid could exist without copper. Aluminum can be used as a substitute for copper in some cases. Aluminum has about half the electrical conductivity of copper. Gold is a useful electrical conductor in cases where corrosion is a concern and price is not a barrier. Iron and steels are still electrically conductive, but only a sixth as electrically conductive as copper. As for thermal conductivity, aluminum, steel, and cast iron can all be used where heat transfer is important, such as cookware. The best cookware has a copper bottom. They might be silver if it's a very expensive piece. In electronics, the best heat sinks are made from copper. Before humans discovered metals and their usefulness, people were restricted to making tools from stone, bone, wood, and other animal and plant-based materials. Modern civilization would not be possible without metals and metallic bonds. And that concludes my discussion of metallic bonds. Thank you for watching. In my next video, I'll discuss ionic bonds.